Okay, so hi everybody. I'm Boris FRANKOVIČ from Statistical Office of the Slovak Republic, and in this presentation I will be talking about Calif, the shiny application for calibration of survey weights. The contents of this presentation will be first to present some background of the tool, then to move quickly around the calibration essentials and optimal strategy, just to know what we are talking about, to be sure. And at the end of the presentation, I will also show some Calif usage in practice. The background of the tool was triggered somewhere around the EU Silk survey, which we wanted to calibrate on more than 100 calibration constraints simultaneously, which was not possible with the tool we used that time. So there was a thought for some powerful tool that can calibrate on many constraints and would be ideally free, effective, comfortable, and also user-friendly with some graphical interface, which brought us to R and Package Shiny as the ideal candidates for this task. But let's move quickly to the calibration. What is the calibration? Let's assume we have a population U with a sample S. Then each unit in S has its own design weight, which is calculated as the inverse probability of selection. These weights need further to be adjusted to account for non-response and, of course, and also the non-sampling errors effects, because without this adjustment, the estimates would be very inaccurate. It is clear that the design weights cannot reproduce our non-population totals exactly. Let's consider we have some population totals, for instance, the number of people living in some area or by age and sex. And these design weights are not capable to reproduce these population totals exactly. So we first apply some non-response adjustment and we get the so-called initial weights. And after that, we seek for some new weights, let us denote them as W, for each unit that confirm the population totals exactly. And these new weights should differ minimally from the initial weights. Then, if we found these new weights, we will use them for estimation. These weights are found by some optimization methods when the difference is measured by some distance functions with the parameter in a form of quotient of the new weight by the initial weight. There are some, or let's say 4 basic methods or different distance functions used for calibration. 2 of them are unbounded. It's linear and raking ratio methods, and 2 of them are bounded versions of these unbounded versions, linear bounded and logic methods. This approach was proposed first by Devil and Sarndel, and it allows for significant enhancement of precision of estimates. But the condition is that the study variables should correlate with auxiliary calibration variables as most as possible. This approach is especially effective when response rates are unequally distributed and correlated with the population variables. And also, at last but not least, this calibration approach can bring us consistency among many surveys. What is the optimal strategy of calibration? It would be quite intuitive that the very strict and tense bounds for the new weights will give us the most feasible solution, because then the difference between the initial and calibration weights would be minimal. But we have to take into account that with the tens bounds, the maximum difference between the initial and calibration weights is smaller, but on the other hand, the limited space for these new weights forces the initial weights towards bounds, and at the end of the day, the average difference between initial and calibration weights is bigger than with unbounded methods. Because less strict constraints form some area to move, where just a small number of weights is pushed off to the bounds, and the vast majority of weights could lay or could remain close to their origins. As a result, the average difference between initial and calibration weights is minimal for unbounded methods. Of course, we want to avoid extreme weights because unbounded methods often tend to very extreme, even negative weights, and it is something we want to avoid. Then we need to use some bounded methods, but the bounds should be in a form of some kind of a trade-off between the width of the interval and the distortion applied. This is how it could look like. On the left side, we have a very strict solution with strict bounds, where almost each of the initial weight is pushed off. And on the right side, we have even bounded, but bounded solution with very, very relaxed bounds. Then just a few number of initial weights is pushed off, and the majority of weights could remain close to their origins. Then the average difference between weights is smaller. The most obvious is the use of the linear function. This is a very boundless method, which allows for negative weights. Then if the algebraic solution exists, then it is always found. Free space guarantees that just the minimum possible number of weights is pushed far away, whereas the majority remains stable. The average difference is thus minimal, and every bounded version and every bounded solution will have a higher average difference. This could be the histogram of quotients. These are quotients of the calibration weight divided by the initial weight. The histogram of quotients with linear method resembles normal distribution. Yes, because the majority of quotients, or majority of weights are very stable and unchanged. This is the histogram of solution with strict bounds, when almost each of the weights are pushed off to the bounds. And this is a feasible trade-off with some level of bounds, but not such strict than the previous one. And this would be the ideal solution. So what are the conditions? The conditions are as follows. The calibration constraints should be reproduced at the first stage. And then the calibration weights should differ not very much from initial weights and lay rather in some kind of a tense interval. The average weight difference should be low compared to the linear method, but we want to avoid extreme weights. And after this theoretical introduction, let's move to the main topic of this presentation, which is a Calif tool. At present, it's fourth version, the Calif 4.0. It's a shiny web application that runs under the GPL license. It is very easy to work with, very fast, and it also maintains some time-proven techniques among calibration tools. The web browser, as usual with shiny applications, acts as a display device, and all computations run locally in R. Nothing is sent to the internet. When we check the GitHub page of Calif, We can browse it a little bit. Here is, for instance, a quite comprehensive manual. Everything you need to know about Calif is written here. So do not hesitate to download it. And of course, here are the source codes. So if you are interested, you can browse it, study it, or even submit some remarks and enhancements, some ideas. It would be great if you could do so. Okay, so please check this GitHub page. The Calif can be run directly by running it from GitHub or by running it from our web page of the Statistical office. So these are the two options. Or even you can download it and run locally from your R studio. Okay, so let's get back to the presentation. The 4 packages are used within Calif. Of course, obviously, it's a Shiny package. The basic bootstrap design CSS is used. Then it's a sampling package with the crucial function Calif. Then the Haven package, the headless package for loading of the SAS datasets. And also the package nlac SLV, which incorporates the solver of a system of nonlinear equations. The main features of Calif are, of course, the web design graphical user interface, very convenient operability, of also two-stage calibration for calculation of integrated weights is incorporated. The data can be loaded very interactively. Calif allows also for stratification. We can calibrate for each strata separately. In the main window of Calif, we can specify the calibration variables necessary to perform the calibration itself. It contains 2 powerful and fast solvers and commonly used distance functions. And in contrast to some other calibration tools, also approximate solutions are possible. So not only the exact solutions, but also approximate solutions. It is a very powerful tool if you calibrate on many constraints simultaneously when no exact solution can be found. You can bookmark your work at any time, check some graphical outputs and many others. What are the requirements? The data structure can be almost free. The data loaded can contain any variables, but at least the calibration variables and initial weights must be included. The required structure for the table of totals is well described in the manual, so please check it if you want to calibrate with Calif. For numerical variables, only the totals are required, and for categorical variables, required are the totals per each category separately. So the table of totals could look like this. When we have some, of course, numerical variables with the grand totals per each stratum, let's say, and then the frequencies or the sum of weights for each category of a categorical variables. So this is just some kind of example. And let's check the Calif itself. So here it is. Actually, it's a navbar page with 3 tabs. The first tab is the overview tab, when you can read the main instructions and some basic information, and you can also set your working directory by clicking on this button. In the data tab, we can interactively load the data. So let's use the test data that are available for Calif at GitHub page. So let us load the data and totals. You can see that they are interactively loaded. You can browse this data, filter, and so on within this window, or set some separators. Let's say if we use another one, we can see that the preview is interactively updated each time. In this case, we want to use a stratification aspect with the region for strata, and the column with weights is called weight. Yes. The numerical variables that will be calibrated could be, let's say, this 12 or even less. It doesn't matter in this case. And of course, it can be some categorical variable called members. When we have everything prepared, we can proceed to the calibration tab, where we can choose some or each stratum. If you want to set different bounds for each stratum, we can do so. But firstly, it is very useful to use the tool, the feature show with initial weights, which calculates the quotient of the Horowitz-Thompson estimates with initial weights and the population totals. So we can directly see where we are prior to calibration. So what are the discrepancies, or what are the characteristics of our sampling population? Yes, it is quite obvious that, for instance, elderly people are more willing to cooperate than younger ones. So we want to calibrate this in order to have everything calibrated at 100%. First, we can run the linear method, let's say. Of course, we get some very inappropriate solution where the lowest weight is in negative values, so it is not quite feasible. But the histogram and everything looks very fine. We can see that everything is calibrated at 100% accuracy, so it's very good, but we need to use some bounded version, some bounded method. So let's say we will use 0.3 to 3, and we'll check what will happen. Okay, and then we'll have some quite nice solution where when everything is calibrated at 100% accuracy, and the lowest weight is positive in this case. And also the lower and upper bounds are in line with what we set in these fields. Okay, so we can see that at the left side, here's a little pressure for the lower bound. If we relax it, we can check if it will help. Nah, not so much. I would say that the previous bound was better. But for instance, what will happen? I will choose only some stratum. What will happen if we set a very strict bounds, let's say 0.7 to 1.5? Oh, then the computation runs for some time, and we can see that in this case the weights are pushed off to the bounds, and it is very non-natural solution. And of course, not everything is calibrated to 100%, and we can get the approximate solution with this. Yes, so we get a solution that is not exactly accurate, but let's say we got the weights that are not too far away from their origins, but majority of them is pushed off, so it is not very good. So we can use some other bounds, and yes, with these bounds it is quite good, so we can save it. Okay, so let's save the solution, and we can check here that for this stratum the bounds used are different to the bounds for other stratum, because we changed for this specific stratum, we changed the bounds, we changed the settings. So we can use any settings for each stratum separately, and the result is the same data set as was loaded, but with one column added at the end, the column with the resulting calibration weight. Okay, so it will be all from my side. If you have any comments, questions, remarks, enhancements, ideas, do not hesitate to ask, do not hesitate to write me or anything. And thank you for your attention.